afternoon will go ahead in the same time, same way of the morning, alternating online, on-site, poster and oral speech. If we are good, we will have sometimes for discussion, but most of the discussion will occur tomorrow. And at the drink and reception and poster session this afternoon, if we are on time at 5:30, then we will have 1 hour and a half of chatting and stimulating discussion today. So here in the same room of the coffee break, we will have drink, snack, and posters. Then social dinner is tomorrow evening. You have chat with Simone. Please confirm where you are coming or not. And then on Saturday morning at 10 o'clock, you will receive tomorrow instruction. There is a tour organized to network, to continue to discuss together while we will watch To the Beauty of Lecce. So we will have a guided tour downtown. Sorry for the people that has to leave before, but that we couldn't do it earlier than Saturday morning. So that's it for the moment being. Now I leave the floor to Shangao that came from China. She's from the National Marine Environmental Forecasting Center, and she will present the validation of the operational ecosystem models and forecasts for the China coastal area. Please, you have 10 minutes approximately. Thank you.
Good afternoon, everyone. Thank you very much for this opportunity to make this presentation in person. Today, my report is about validation of operational ecosystem models and the forecast for the Chinese coastal seas. It contains 4 parts. Firstly, it's Chinese global operational and oceanography forecasting system has been updated for recent years. The domain became larger. It includes global ocean, North-West Pacific Ocean, Indian, East China Sea, South China Sea, and Polo. And the resolution are more refined. It extends from 10 kilometers of the global ocean to the 1 or 2 kilometers of the coastal seas. And this is the update of this system, which we compared with the observation other models, and update some data simulations such as ENOI or 3D WAR. According to the IVTT Class 4, the global high resolution forecasting model with the NEMO, which gives good performance, such as the SST, SLA, and the TS perform. TS perform maybe a little poor. And the Northwest Pacific Ocean, this model we update the ENOI for SLA and the 3D WAR for TS Argo. East China Sea forecasting system, it is update 120 hours for casting products, and ENOI for the SST. Compared with buoy date, it improved 60.5% almost. And the last part is the South China Sea forecasting system. The updates is about bathymeters and the grids. Some grids are refined in the coastal lines. The other may be larger in the open sea. And recently, we updated we have the version 2 of this South China Seas model. The current and the temperature shows better than the version 1, such as we can see in picture the red picture. And the second part is the marine ecological forecasting system. As we know, different seas has different environmental parameters. So based on the hydrodynamic model, we also coupled with the marine ecological model for the forecasting. It consists of Bohai Sea, Yellow Sea, East China Sea, and South China Sea. Different seas have different ecological parameters, such as the Bohai Sea and the Yellow Sea. It is a very small sea, and it includes 8 rivers and 9 rivers and 8 major consistent of tides. And we, because the observation data is very enough, so we just found a lot of the dates and observation data can compare with our this model, and we calculated the correlation coefficient and the RMSE. Some shows better, but some maybe are low with the observation date. And this is the prediction of the chlorophyll, DO, and the pH. And this is the product of the ocean of the forecasting. The period of forecasting is 5 days, and the vertical layers include surface 10, 20, and 15 meters. Yellow Sea and East China Sea, it includes 7 rivers and 8 major constant of tides. And in terms of the variation of the nitrate chlorophyll and the correlation coefficient between the simulation nitrate and observation data is about 0.8. And at the PC section, the correlation coefficients can reach over 0.9. And also the chlorophyll and the chlorophyll shows the spatial and the seasonal patterns with observation. But the R value is 1.62 and 1.83 in autumn. And this is the products we focus on the Yangtze River. And the South China Sea, because it had a large along coastal seas and deep basin, so we found the 21 rivers in this model and 8 major constant of tides. And this is also the variation of this model, chlorophyll or DO. And in recent days, we just updated this system. It shows better in the coastal seas than before, and we can see the model and it compared with the remote sensing data. In the surface layer, the RMSE can reach 0.8 1, 2, and the other layers also shows the good result. And this is the products. And we also have some coastal base. It has different conflicted environment, and also do some validation and the products for some special users. And we also want to try to analyze the verification and the evaluation of forecast results. For example, for BELS, RMSE, model BELS, and model efficiency, cost fraction. Because this different model have the same model, but use the different parameters. This is the result. Assessment index is excellent, very good, reasonable, poor, respectively. Some shows better, but the other one maybe shows not good enough. And we need to improve this class. And we also and we need to a long observation date. So we just found the two buoy state can do comparison for 1 year. So some data is sometimes have this data, sometimes the data is not well. And we also establish the ground form display. We can check the website to see the products. And the third part is about mass conversation ocean model. This is MICOM. This new model is developed by our central. What is mass conversation ocean model? It is the key features is the mass conversation, and we want to have a simpler numerical model for forecasting. The model only have 2,000 coastlines now, and the control model coastlines below 4 millifill. And first we ready for the GPU, and the next we ready for KM. And this model framework it's based on the vertical pressure coordinate, and it has multiple grids to choose, and the multiple grid support without changing the code. And it runs very fast, and it has petrol I/O acceleration, and GPU based on the open ACC. And this is the key features of the Michael to compare with other models. And we do some evaluations of the Michael with NEMO, and it shows a good results. And the other, it is the vertical of forecast products of temperature and salinity result. In this year, my work is to coupled with the model MICOM with the biology chemical model. It almost finished the code comparing, and we try to do some simulation in the ocean, in the global and the West Pacific Ocean, Northwest Pacific Ocean. The last part is the future innovation. Yes, in the future, we need to face the new challenges such as super data, super computing, intelligent forecast to improve our forecasting of products, and the history forecasting data, how to implement to get compare with the history observation data is our need our work to do in the future. That's all. Thank you for listening.
Thank you very much. We have time for one question. Yes, please.
Thank you. Just please, can you specify which ecological model have you used? Do you develop your own ecological model, or do you use an existing one? And could you specify if you use the ecological model in online or offline?
The hydrodynamic model, we use ROMs for the coastal seas, and the global global model, high resolution, we use with high resolution we use the NEMO, and the ecological model we use cosine 15. And
Is it online couple?
We run together. Yes, it's a large computing because we use lots of machines.
I want also to give one question. How do you treat rivers? Do you have rivers modeling? River modeling?
No, we just give the river for the open boundary.
Okay. Thank you. So next presentation is a poster and is Pencheng Wang from Canada. Pencheng, are you?
Yes. Can you see my screen?
Yes. Can you share your screen?
Okay.
Because it's easy for you to
Yeah.
it's there. So
yeah, it's there. Okay.
Please go ahead.
Okay. Thanks, Giovanni. Okay. Hello, everyone. So I'm Pencheng Wang, research scientist from Environment and Climate Change Canada, ECCC. So at ECCC, we do research for storm surge modeling. And today I will talk about ECCC's global deterministic storm surge prediction system. This global system was recently developed to provide total water level forecast for all Canadian ocean coast. The first version is barotropic, and based on NEMO, it has a 1/12 degree resolution. In this work, we attempt to further increase the complexity of this system by including the effects of volcanicity and the sea ice, while also keeping the system sufficiently efficient so it can also be used for ensemble forecast and climate studies. So on the left, I show the work for adding volcanicity. So the method is based on a weak nudging or model the temperature and the salinity to external fields provided by a causal resolution data assimilative ice ocean model running operationally at ECCC. And this nudging allows us to absorb the low frequency variabilities from the external model, while also allows the higher frequency variability to evolve freely. And the nudging also allows us to further reduce the vertical levels to only 9 levels. And overall, this only results in 10% additional computational cost compared to the barotropic one. So here shows impacts or adding volcanicity on predicted water level. And here you see that from blue to red, you see the decrease with the MIC values for different water level component. And this map further shows the spatial improvements, spatial distribution with the improvements in the tidal residuals. And part of these improvements can be explained by the baroclinic effects on coastal tropical waves. And to illustrate this, I will show the propagation of the signals as a function of the alongshore distance and the time along this alongshore coordinate on the west coast or North and South America. And clearly we see that the model captured multi-scale baroclinic signals propagating either side of the equator up to 15 centimeters, but I note that it can be much larger during strong stormy winds. For the CIS effects, we developed a new parameterization of the ice ocean stress, which features a transfer function that is used to represent the tidal component with the relative ice ocean currents, ice ocean velocity. And so this transfer function allows us to circumvent the inconsistencies in tides between the present and the external models. And here in this figure, we show the impacts of adding ice on the seasonal modulation of the tides. On the left is the M2 amplitude, on the right is M2 phase. Top is without ice, middle is with ice. And clearly we see that adding ice generated much stronger modulations. And this is consistent with the observations shown by the circles. And their composition is also plotted here. So to explain these results, we found that they can be understood by a combination of both direct and indirect effects with the under ice friction. And this indirect effect is associated with a shift with the tidal amphidromes. And these shifts are plotted here in this panel, and you can see the shift with numerous tidal amphidromes. It can be more than 100 kilometers for the system in the Eastern Siberia Sea. And these shifts are well predicted, and they all tend to shift to the coast where you have the strongest tidal dissipation. So lastly, we look at ice effects on storm surges, and we see we show the results and 5 permanent tidal gauges in the Arctic and Hudson Bay. Observations in black, red is with ice. And we see that adding ice leads to great improvements by attenuating the peak surges up to 1 meters and station Tuktoyaktuk, which is located in the Arctic Ocean. So lastly is a brief summary. So in this work, we have developed efficient ways for adding vacancy and CIS effects to the water level systems by taking advantage of the external fields provided by advanced data assimilative ice ocean systems. And this leads to great improvements in the forecast scale with the total water level. And also we try to understand these improvements, and we provided physical explanations. Thank you. That's it. If you want to learn more, here are the 2 references.
Thank you very much. Thank you very much.
So I will stop sharing.
Question? I have one. Did you compare with the higher resolution models and storm surge higher resolution model, the performance of your model? And the second question, do you have a data set of your results available for public, for studies?
Yes, Giovanni, for the first question, before that, this global system, we have a high resolution system on the East Coast, which is 1/30 degree. So we found that it's comparable and even better during some events. So for this reason, we use this system to replace the high resolution regional system on the East Coast of Canada. The second question, the second question, the data is available, the observation data.
Thank you very much. It's a pity you couldn't come in lecture next time, maybe.
Yeah.
Okay.
Thanks.
So, sorry, there's Nadia with one question.
So very interesting. We also believe you need to do baroclinic models to get the level of accuracy of storm surge that is required. What is the reason in your case? In our case, we found that coastally trapped waves that were induced by shifts in the Gulf Stream due to the hurricane going. So what is, in your opinion, the effect on the coast that you see and that's due to baroclinicity? Where does it come from? Does it come from the open ocean, like in our case?
Like on the west coast or North and South America, they are both, I would say they are both from the open ocean and locally generated. Some of this come from the equatorial waves that transform when they propagate into on the west coast, they transform into coastal trapped waves and propagate to either side. There are also locally generated baroclinic waves, which I see like at some islands, and it's like baroclinic internal waves. And it's also strongly affected by the waves or the shelf. The baroclinic effects tend to be stronger on a narrow shelf because where there you will have a large Berger number. So the coastal trapped wave tends to be baroclinic.
Thank you so much, Pencheng. Thank you.
Thanks.
So next presentation is by Donata Cano from OGS, and it's online. Donata couldn't do it.
Yes, I'm here. Can you hear me?
Very well.
Yes. Are you seeing my screen?
Yes.
Yes. So
yeah.
I'm now in the
Very
presentation
good.
mode. Is fine?
Try to keep in the 10 minutes. It's perfect. Go ahead.
Yes, okay, I will do my best. So first of all, it's nice to be here with you, even if I'm online. I'm sorry for this, but it's a pleasure to participate to this very, very interesting meeting. So today I'm going to talk to you about a recent application done to the Venice Lagoon in the frame of the Venezia 2021 research project, and also in building tools for the Danubius research infrastructure. The title is Schiffing by FM for the scenario analysis in the regulated Venice Lagoon system. And the outline, I will briefly present the Schiffing model implementation to the Venice Lagoon and tested with observation for 3 years. 2 climate scenarios for SCP 8.5 and 4.5 using projected downscaled meteorological forcing and boundaries. And then the simulation of human regulation of the mobile barriers, so the Mose closures that are meant to protect the city of Venice from the flood events. And results regarding the climate scenarios and the Mose implementation on biogeochemistry. So where is the Lagoon of Venice? Is located in the northern part of the Adriatic Sea, as you can see. It's a lagoon 550 square kilometer wide, made of islands, wetlands, and tidal flats. It's crossed by several channels. Its average depth is 1 meter. It is connected with the Adriatic Sea through 3 inlets, and it receives also fresh water and nutrient inputs from 11 rivers from the mainland. Understanding the human pressures depicted here is very important, and understanding how they interact with the biophysical system is needed to assess how this human interaction affects the ecosystems and ecosystem services. So understanding and simulating the biophysical system and the inputs and interactions with the boundary and with the human forcing allows us to make scenarios and to understand how these systems interact together. So we build our model, also including the marine boundary conditions, the forcing, meteorological forcing, and the inland inputs, building our input data sets. This is another overview of our system. Of the Scheife hydrodynamic model has been coupled to the BFM, that is the biogeochemical model that simulates up to 53 state variables representing the cycle of carbon, nitrogen, phosphorus, and silica, and the phytoplanktons divided in 4 groups, and zooplankton, and represented that are representing different functional types. Moreover, the model has been offline connected to a clam growth model simulating the growth of clam, resource that is harvested in the Venice Lagoon. We had a huge amount of data that are used to test, calibrate, and also to the testing of our model. The implementation, we use the Scheife in 3 dimensions with a mesh made by 7,000 nodes and 7 vertical levels. And we set 3 Heinka simulations for the 3 years listed here, and through 2 scenario simulation for the 2 RCP 8.5 and 4.5. In that case, our model was forced using regional downscaled models for the meteorological conditions, and also using the the projections done for the climate scenarios for the Mediterranean basin, done with NEMO and OGSTM. And in addition, we added also the MOSE closures. Here we can see how the closures are projected to increase toward the ends of the century. Here we have the time in hours of closures. That means that at the end of the century, in the worst scenario, almost every day, the lagoon is closed for at least few hours. So the model was tested and calibrated and then tested. Here, for example, we can see for different station the evolution of the oxygen concentration of the model depicted in blue, in the line, and compared with the data. In the right side, we have a map showing the spatial variability. And again, we have in dots the oxygen measures, compare the average oxygen measures on March 05 compared to the average of our simulations. As an example, here we can see different variables for a station, 9C. And so the model is behaving quite well. Also, it reproduces the spatial and the time variability of these different state variables. Here we have the chlorophyll, for example. The model was also used to compute trophic indexes. Here we have, for example, a comparison between the 3 years for the TRIX index, that is an index that shows the trophic state of the lagoon waters in April, compared also again in dots with the same index computed from the data. Climate scenarios. Going to the climate scenarios, we see that, as expected, we have an anomaly regarding the temperature. On the left side, we see the monthly average temporal anomaly in the mid-term future, 2050, right side, far future, 2100. We also see that the model reproduces the acidification of the system. Interestingly, this acidification is higher than that is projected for the Mediterranean Sea. This highlights the importance of downscaling and making a high-resolution coastal models to better understand the specificity of the coastal processes and expected coastal processes. Again, we have another anomaly between the mid-term future and the present. And this is the anomaly in chlorophyll. We see that the chlorophyll decreases in the central periods of the year. So, and we have an anticipation of the bloom. The system is, as a synthesis, less productive, and this is shown also comparing the TRIX index and the chlorophyll A concentration reproduced by the model for the present states that you can see here, compared to the future that is here. We can see that the system under this assumption and our scenarios appears to be less productive. As an example, then on the extreme scenario 2100, so far future, I'm going to show you the differences between the simulation done with and without Mose closures. Again, we see that are some differences. These differences are not unequivocal. In that case, we have the lagoon that is experiencing different anomalies in different locations. That means that the habitat in the lagoon itself are going to change a little bit their conditions due to the operativity of the Mose closures. That was for oxygen. Here we can see the same for the chlorophyll. So the impacts of the Mose closures on the chlorophyll concentration in the different months at the end of the century. Then we projected the impacts on the clam, again, using the biogeochemical output in different places. We see that there is an impact on the clam productivity. So concluding, we used this downscaled high resolution model to project the state and evolution of the biogeochemistry of the Lagoon of Venice under climate scenarios and under Mose closure scenarios. The projected change show that the lagoon conditions are expected to change. So we projected an impact on the lagoon ecologies from individual to community to habitat and to ecosystems. And I'm here for your questions. And thank you.
Thank you, Donata. Very nice. Any question? Yeah, Joanna Staneva is posing you a question.
Thank you, Donata. Very nice presentation. I have two questions. The first one is, what are the data of nutrients and other biogeochemical parameters from the rivers for the projections? And the second one is, have you considered the uncertainties in the projections, for example, through ensemble simulations, or are there plans for that?
Yes, of course, here I didn't have much time to go in depth, but yes, we made different simulations. So basically we did a simulation, a first group of simulations, keeping the nutrient as they are now, and the river discharge as it is now. Then we projected a change in the river freshwater discharge according to the precipitation, so doing statistical regression, and keeping again the concentration of nutrients as it is. So not the total amount, not the total, but the concentration. In that case, and this is the projection that I show here today, the total amount of nutrients is decreased due to the fact that the freshwater discharge has decreased. A third simulation instead was done using again the projected river discharge based on precipitation pattern, but keeping the total amount of nutrients. So this was our solution to this very, very difficult question.
Thank you, Donata. Thank you. We have to move to the next presentation.
Yes. I just wanted to add that if you have a further question, there is Ginevra in the room, so you can discuss with her that she can. Okay, and thank you and bye.
So, thank you, bye, Donata. In my list, there is even Federico now. Is it true? Okay, good. Next is Ginevra. Sorry, I don't know why we end up like that. I guess by chance. So even Federico is at CMCC. He's working just one floor up, and he will present our activity on storm surge model forecasting and the attenuating role of nature-based solution. Please, Ivan, you have 10 minutes. We have,
yeah,
sure.
Okay. So thank you, Giovanni. So I'm going here to present this activity related to the storm surge modeling and the role of nature-based solution. We have three keywords in this presentation: storm surge, the flooding, and the role of seagrass meadows that will be modeled in some of our test case. The presentation is basically organized in three parts. First, the first introduction on our coastal modeling capabilities, our coastal modeling, downscaling, and also relocability for operational short-term forecasting. Then the second part, which is dedicated to the storm surge modeling. And in particular, I'm going to first introduce test cases that we have done recently in for what concerns the Medicane formed in the Mediterranean Sea, the hurricane formed in Mediterranean Sea, the Medicane Janus, and we want to account what is the contribution of waves at the total water level. Then a second test case, which is in the Adriatic Sea, and we will deal for the event of November 2019. And here we want to have a look at the flooding extent in a region of central Adriatic Sea in Gulf of Manfredonia, and then want to look at the attenuating role of nature-based solution in the area of Venice Lagoon. Then conclusion, of course, future step. Let's start first with the downscaling capabilities, starting from the Copernicus products. In the last year, we have implemented several models in different regions of the world ocean, mainly in Mediterranean Sea, but we will have also other implementation in extra European seas, and we have used also the concept of relocability to do this type of implementation. And I show just some example of application that we have done recently, starting from the first one, which is dedicated to the river ocean continuity for the area of Western Med, Italian coast of Western Med, other application that were dedicated to the Gulf of Taranto, where we support operation for what concern oil spill modeling, other application for the entire Adriatic Sea, which has been developed in the framework of Stream Interact project, and were oriented specifically to storm surge. Then we have again river sea continuity in the area of South Atlantic Bay, Bight in area of Georgia. We have seen some slides also in the presentation of Nadia for the simulation of the storm surge induced by hurricane. Another type of application that we have done is for the Turkish Strait system, which represent one test case of downscaling and upscaling, since we reserve a boundary condition from the Copernicus products, from the, in particular from the Black Sea and the Mediterranean Copernicus products, and we get back the condition to the Black Sea forecasting system. Last implementation that I'm going to show here is for the area of Dubai that we developed specifically in the period of Expo, where we participate and we provide forecasts for this area. This is an introduction for what are the model capability related to the coastal downscaling and relocability. Now we are going to look at the specific application for storm surge, and we start with the Medicane Janus. I don't know why the presentation is going in this way. Okay, but the Medicane Janus has been here modeled with two set of models. One is the Wave-Watch 3 model, and the second is SHIFAM. In this case, SHIFAM model is forced by the Wave-Watch 3 by means of radiation stress, and we want to account what is the contribution of waves to the total water level. And here we have the track of the Medicane that impacted the coast, the Greek coast, and the area of Zakynthos and Kefalonia. Here we have the animation of the simulation that actually is not working, but you can imagine that here we have the formation of the wave and the generation and impact then in the coast, and the same for what concerns the sea surface height. The model has been validated both for what concern the waves and the sea surface temperature, the significant wave and sea surface temperature with the track, with the satellite tracks. And here we have the a long track validation with a slight overestimation of the peak, but with a satisfactory normalized root mean square error of 14%. For what concerns the SST, this would be an animation that would show the fingerprint of the medicine, so the cooling of the medicine in time. But it's important to see also at this comparison with satellite. Here we have the difference between post and pre events that show this fingerprint, this cooling in the satellite that is quite well reproduced by the model, even some differences in terms of a more diffused fields, for instance, but we are satisfied by this open ocean, let's say, comparison. And looking then at the coastal scale, what we have here is the comparison with the tide gauge, where we would have a look at the observation that is represented by the red lines. The green line is represented by the simulation with the SHIFM only, so only circulation model, while the black is represented by the model that is forced also by the waves. So as you can see in the stage of the peak event, we are very close to the observation, and we improve the accuracy of the model up to 20% at the peak. Also in the decay stage, you can see that even SHIFM has some difficulties to look at the decay stage. The value of the SHIFM forced by Waywatch 3 model is closer to the observation. Then, apologize for the figure, but I don't know why it works in this way. But then I would show also the map of circulation that, of course, resemble the pattern of the hurricane impacting the area, and the area where we have the higher sea level, which are in this area of Etolia-Acarnania, which are areas that were impacted by flooding. We have seen different other papers that has been some downstream chain with the flooding model. This is for what concerns the part of wave contribution to the total water level, and then I'm going to show another application for the Adriatic Sea that we have developed in some projects such as Stream Project, EO at Sea, and also West Coast, where we investigated the event of November 2019 in Venice and in Gulf of Manfredonia. This event occurred in November, and in particular in Venice, we had a large part of the city that was flooded. And for the first case, the one on Venice, we have done a look. We have tried to look at the seagrass meadow, how can attenuate the storm surge. For the second event, we have built an operational forecasting chain dedicated to the impact forecasting to look at the flooding. In particular, for what concerned the event of November that we have run for the area of Manfredonia, here, considering the model X Beach, we have, of course, designed this model with a very high resolution digital terrain model, and with the roughness and land use map that are the two main drivers for a flooding model. And we have simulated the event to have a look at what are the extended area of flooding. And in this area of Margherita di Savoia, we have an extended area up to 1.5 kilometers that has been flooded. Now we are working to better calibrate and, of course, validate this event using also satellite data in the project EO at Sea. Last slide is on the on the event of November and the impact in Venice. And here we have designed the model that is at a very high resolution in the area of Venice. And we have enforced and enhanced our model also with the coverage of seagrass that are present in the lagoon, mainly are Zostera marina, and also the coverage of marshland areas. And we have performed for this event 2 simulations, one without vegetation and the other with vegetation. And we have done a look at the sea level. And as you can see here, you have the value of sea level that decrease even is up to here. The maximum is 140 centimeter of sea level. You have up to a maximum of 7 centimeter of sea level that is decreased, so up to more or less 5%. The same pattern could be is shown also for what concerns the bottom velocity, with the decay of bottom velocity in the case of vegetation that are included. Okay, just to conclude, yeah, we have shown some implementation that we have developed in terms of coastal downscaling, mainly oriented to the storm surge forecasting. We have shown 2 events, one for the Medic and Llanos, and the other for the event in Adriatic Sea of November 2019. And we have shown both the capacity of model, also the forecasting impact, so the flooding, and the role of nature-based solution to attenuate the storm surge. Of course, we have different other steps to take that are in advanced also with the interaction between the wave and currents, and also advanced also with the wave, current, vegetation, and sediment modeling framework. So that's all. Again, I apologize for the, maybe it was converted in PDF. I don't know why.
It was perfect. It was very nice. Do we have a question? Each time I see one presentation, it comes to my mind another idea. So I will repeat.
Thank you. My name is Lydia Pushtar, and I'm from Croatian Med Service, Marine Operational Forecasting Service. And I wanted to know, did you think about validation of this second event by using data from the eastern side? Because as I recall, we had the highest waves measured near Dubrovnik. I think it was near 11 meters. And also we had some very high levels, sea levels. So
yeah, unfortunately, up to now we have just validated the let's say the western side of the Mediterranean Sea. We have done some validation with the satellite track, but of course are not oriented to the really coastal zone. It would be nice to try to foster an exchange of data to try to validate also with data for the Croatian side.
Thank you.
Eastern side.
Great. Thank you, Ivan. I think we stop here with the question. Now it's the time of Ginevra Rosati from OGS. You have 5 minutes for the poster, and of course, then the poster is.
No, I have.
No, then sorry, I got confused. You have a presentation. I start with Ahel.
Hi, everyone. Oh, my presentation is about new tools for assessing contamination in coastal and marine environments. Mercury is a persistent pollutant of global concern, which is found in natural waters, mostly in 4 species. Inorganic species are oxidized mercury and elemental mercury, while organic species are bound to 1 or 2 methyl groups and are called monomethyl mercury and dimethyl mercury. And together they account for concentration of methyl mercury. Elemental mercury and dimethyl mercury are gaseous species which tend to evade to the atmosphere, while oxidized and monomethyl mercury are reactive species that complex to particles, dissolved organic compounds, oxides, and ions. All these species are interconnected through biogeochemical and photochemical transformation. We are particularly interested in processes leading to methyl mercury formation because this compound is neurotoxic and is taken up by phytoplankton, and then it is bioaccumulated and biomagnified in food web. And this poses a concern for ecosystem health and also for human exposure through seafood consumption. Back to 2009, it was found that methyl mercury in the water of the Mediterranean Sea has a nutrient-like distribution. You can see in the plot here on the right, on the left, that the vertical profile detected resembled those of phosphates, and this was attributed to the methylation of inorganic mercury during the remineralization of sinking organic matter. In the same year, in the North Pacific Ocean was observed that there are a significant relationship between concentration of methyl mercury and apparent oxygen utilization, as well as with organic carbon remineralization rates. And now we also have data for the Mediterranean Sea confirming the correlation with apparent oxygen utilization. These data are only for water up to 600 meters depth. Sorry. In the plot here on the upper right, you can see the concentration of methyl mercury in the Mediterranean Sea in the western and eastern basin. And you can see that they resemble the gradient of primary production decreasing from west to east. To simulate these dynamics, we couple a model for mercury biogeochemistry and bioaccumulation to the existing framework OGSTM-BFM model, where OGSTM solves the physical transport and BFM is the biogeochemical model. With this model, we were able to reproduce the observed zonal and vertical gradients of methyl mercury distribution. And the model also pointed out that the distribution of methyl mercury in plankton is decoupled from the distribution of water, with also differences between phytoplankton, that is shown here, and zooplankton, thus confirming the need for new tools in interdisciplinary integrating different information. This work was published last year in Biogeoscience, so you can find it if you're curious. But what about coastal settings? As I mentioned before, some mercury species have high affinity for particles, which lead to their accumulation and in coastal sediment, and possibly to secondary emission from sediment to the water driven by the benthic pelagic coupling. Thus, in these settings, dynamics can be strongly influenced by historical or ongoing contamination and by sediment dynamics, so if net deposition or erosion is occurring. The abundance of inorganic sediment and refractory organic matter also change the bioavailability of mercury species for transformation. Sorry. In the plot here, I don't go into details, but was a preliminary assessment for the Venice Lagoon, where we reconstructed the input and output from the pre-industrial to post-industrial phase, and you can see modeled reservoirs for water and sediment. To assess this dynamic of the Venice Lagoon at a higher spatial resolution, we developed the Scheiffen-Mercury model by coupling the hydrodynamic Scheiffen model with a model for mercury biogeochemistry and the model for sediment that solved the benthic pelagic coupling of mercury species and particles, and also track the morphodynamic evolution of the seabed. In this plot, you can see how the modeled state variables respond to different meteorological conditions. So in the upper panels, we have a day of high turbulence. In the intermediate panels, it's a day of intermediate turbulence, and below a calm day. So you can see that inorganic mercury, silt here, and refractory POM change quite visibly between the 3 days, while for methyl mercury there is much less variability because methyl mercury is less bounded to inorganic sediment, so less affected by resuspension. Here you can see the model results average and compare to the values given from a comprehensive assessment that was carried out between 2001 and 2003 by Bloom and colleagues. We can see that the model reproduced quite well concentration of total mercury in winter, but tend to underestimate strongly both spring and summer concentration. And the summer estimation is also true for methyl mercury modeled concentration, while for methyl mercury, the other season are slightly overestimated by the model. So the underestimation that is occurring in summer is likely driven by the underestimation of suspended solids in the water that you can see here. In the upper plot is total suspended matter. The line is the model and the box plot are the data. And you can see that the upper values are between July and August. And below it's just organic matter. As was found by previous author, this is a characteristic feature of the Venice Lagoon, which is, however, driven by the increase of anthropogenic activity during summer due to the shallowness of the area. So this dynamic is not taken into account by the model right now. Here we have the variation after 1 year of simulation of moderate concentration of mercury and methyl mercury in the sediment, which is driven by the resuspension, transport, and deposition in other areas of mercury species associated with the sediment. And in the panel C here, you can also see how the sediment itself change in thickness in response to erosion and deposition. While below, you can see the initial condition for mercury and methyl mercury, and also in panel C, the mask that we apply to reduce sediment resuspension in areas that are covered by vegetation, so both seagrass meadows and salt marshes vegetation. So to conclude, we have developed 2 new tools to assess the fate and transport of mercury at different spatial scale. This model focused on different processes depending on what is more important in each ecosystem. But we foresee that in the future we could integrate the 2 models also in the light of what Donato showed before. We already have performed a coupling of Scheiffen and BFM, and we can put all together at some point. And also very important, this framework can be extended to other pollutants when the dynamics are a little known at least. Thank you.
Thank you. Thank you very much. Congratulations. Any question? Yes, Nadia.
Yes, thank you. Very interesting. So how relocatable and or usable is this approach for other pollutants, and how relocatable is for mercury?
Very good question. Thank you. Well, we haven't tested in other sites because everything is quite new. For the model that we use to the Mediterranean Sea, there are similar global applications. So I think that it can work. For what we have done with Venice Lagoon and Sharpe model is more new. And there is more work from us really to find new solutions.
In the coastal.
Yes, in the coastal application, it's nothing like this has been done before. So I would be really curious to test this. And for other pollutants, I think it's very feasible because the biogeochemical cycle of mercury is very complex. It has a lot of process. So ideally, we should just remove process and adapt the coefficient, the rates of the transformation and stuff.
And what, can I ask another question? What is the need of observation? Do you have a sense of how much, what is the observational requirement for, bringing this model in another area?
Yeah, this is a very weak point with pollutants. We have not many data, and it's difficult to validate the model. Like, we have made the kind of comparison, but we cannot say it's validated because the analyses are very costly, much more than for nutrients and other variables. So we need more assessment that show us how the dynamics varies seasonally and with space.
So we should also develop the sampling scheme and the type of measurement for validating.
Yes, I mean, there is a community for mercury that is working hard to collect new data because there is also under the Minamata Convention a big network, international network. Now we are actually more focused on trying to aggregate Mediterranean data, which are more abundant. While at the coastal site, yes, it's more sporadic.
I think we should, at least in Italy, there is a network, the existing network of ARPA, which is measuring also pollutants like mercury.
Exactly.
So I think we should do an effort for the coastal area to gather these stakeholders. Otherwise, we will never at least exploit what it exists. But I know that Nadia, myself, and Ginevra could speak about this for a couple of hours more, but it's not possible. So now we have Sara Morucci.
Thank you.
Thank you very much. Online. So please, Sara, can you share the screen? No.
Yes,
Share. Gianni, dobbiamo togliere la condivisione.
Sara, can we present your presentation or would you like to share?
No, it's better.
No, I prefer to do by myself. Thank you, because there are some modifications. Can you hear me?
Yes.
And can you see my screen?
Yes. If you can stay in 10 minutes, Sara, it would be
maybe I try, but I don't know. So thank you very much. And first of all, I want to apologize for not being with you in Lecce, but thank you for this opportunity to show you something about our forecasting system and what's going on, especially related to the managing of the uncertainty related to storm surges, well known as Acqua Alta in Venice. This is the result of work in collaboration with Gabriele Coccia, that is the real developer of the tool I will show you in a few. And this is a brief overview about what I'm going to talk about, the sea level, how to face storm surges, why we need to move towards a probabilistic forecast, the tool that is the model conditional processor, and some results about the application to one case. This is a description of ISPRA integrated marine operational system we use to forecast storm surges, especially in the North Adriatic Sea, in the Venice Lagoon, and it is composed of two main components. The forecasting one that is Scheiffen based, and the other one that is the national monitoring system that gives in situ data used as for the calibration and validation of models, as well as for the data assimilation in real time, in order to be able to follow and to improve the forecasts of sea level. And this is these are the maps representing the 36 stations distributed along the Italian coast from belonging to the RMN, the national network, and the other one is the map of the 29 stations, all concentrated in the North Adriatic Sea and in the Venice Lagoon, obviously because we need a very capillary and detailed information in order to be able to follow what's going on during a storm surge. This is the representation of the map of the grid related to our Scheiffen model implemented and with a resolution that is, as you well know, developed by CNR ISMER and with implemented in our operational chain with the resolution ranging from 40 kilometers in the Mediterranean Sea up to hundreds of meters in the lagoon, in the Venice Lagoon. And we run every day in our operational chain the Scheiffen model with many different configurations, depending if we use the data simulation in real time to improve, as I said, the forecast, and depending of the input, the meteorological input we used, because we use as the ECMWF as well as the VOLAM meteorological information. Why to forecast? Just a picture, because it is well known that the Venice Lagoon is increasingly exposed to the phenomenon of storm surges. And when I say increasingly, I mean not only in terms of frequency, but also in terms of intensity, magnitude. So, moving on, this is the focal point of this presentation, because we are moving from the deterministic point of view towards a probabilistic focus. Not only us, but we are trying to do this in our case. And why? Why the need to move towards the probabilistic forecast? Because when we are dealing with storm surges, in this case, and floods, and especially in the North Adriatic Sea and in the Venice Lagoon, let's say we cannot avoid this phenomenon, but what we do is trying to predict them sufficiently in advance to be able to protect this critical area. But doing this, we necessarily have to deal with models that are, even though they are the best models we can have and can apply, they are always imperfect, and then the uncertainty still remains. So what we can do with this uncertainty, and how we can translate all this information, this knowledge about the uncertainty, into an effective intervention strategy. But first of all, moving back, we have to be clear that we have to be sure that we are referring to the predictive uncertainty, to the uncertainty as the same concept, because I'm quite sure that if I ask you what it is, the uncertainty in your mind, in your thought, probably I will receive many different answers depending on the thought you have, the meaning you give to this word. So for someone could be the performance of the models, the forecasting models, for someone else the error of the models. But in this work, we are referring to something different, specific, and we are referring to the predictive uncertainty as the predictive probability distribution. What I mean is the probability of a sea level and exceedances an occurrence to happen in the future, conditional on all the information that we have in the present on this possible future realization of the sea level. So what we are trying to do in this work, what Gabriele Coccia, that is the real developer of this tool, tried to do, it was to understand in which part of the world we are moving, because if we could be in the perfect ideal world, we can move in the delta of Dirac. We could have a delta of Dirac representing the perfect, no uncertainty. On the other hand, we could have the total uncertainty, but what we are trying to do is to understand which is the shape of our predictive uncertainty, the probability distribution of our data, of our observed data with respect of the forecasting models that represent in the present the best knowledge we could have on which could be the future realization of the sea level. So this is the model conditional process that has been developed by Gabriele Coccia, and starting from the historical time series of observed data and their prediction, we could try to understand which is the joint probability distribution, but in the real space it is not a normal one, so we have to convert it with some trick in the normal space using the normal quantile transformation. I don't want to give you too much details also because I'm just a user, and in this normal space it could be considered, this data could be considered, the joint distribution could be assumed to be a normal bivariate distribution because we are dealing just with one model. Then we can we can evaluate the predictive uncertainty, this probability distribution, and then we can convert in the real space this distribution. So finally, we could be able also to predict which is the probability to exceed the threshold, and this could be computed as the integral above the threshold value itself. So this is the generalization in case we have more than one model, and so we have the Bayesian combination, and we can have not just a binormal distribution, but the size of the distribution depends on the number of the models we are dealing with, and the same happens if we consider not each time lag at once, but altogether the time steps given by the forecasting models. So when we obtain the MCP in its multitemporal, multimodal configuration, we could be able to answer to these questions. So which is the probability that sea level could be higher than the threshold at exactly one time lag in the forecast time lag, as an example, the 24 hours, or which is the probability that the threshold could be exceeded within the next 24 hours. So we applied, and these are the main results. This is a case, I will show you just one case in which we applied it to Punta della Salute historical time series, as well as to Lido di Gasud, because since 2020, it started to be elevated Mose barriers, as you as well know, as trivial. In Punta della Salute historical time series, a lot of the peaks has been flattened by the Mose elevation. So we can use data in Lido di Gasud that could be considered, since it is on the coastal area outside the Venice Lagoon, it could be considered such as a sentinel of what could have happened in Punta della Salute without Mose barriers. So on the left side is just a scheme representing the models, our Scheiffen configurations. We have 8 different configurations depending on if we use ECM WF or model or Bolam input data, and if we use or not the data simulation. And these are the different configurations of the MCP we performed on different periods 2018 and 19, just 1 year, because these are is the available period for data, and the validation, the period 2020-2021. And these are the preliminary diagnostic results about the of the MCP. Here are represented for the calibration on the left side and the validation period on the right side, the cuckoo plot. And as expected, if we have the optimum behavior of the MCP, we expected all the observed data to be distributed with respect to their forecast one all along the diagonal in this picture. And the S shape means an overestimation of the variance and the inverted an underestimation. And here you can see for different time lag, 8 hours up to 96. Here is presented the mean absolute error with respect in blue for the MCP with respect to the different models, Scheiffen models. And we can observe that the blue bars are always lower than the numerical models. And then for numerical models. The goodness of this index reduces as usual, moving on with the time lag, as the time lag, the forecasting time lag increases because forecasts get worse. And in this case, we could have also a lower a reduction in the goodness, depending on the storm surges, the extreme events that has been observed during the calibration period. And this is the mean bandwidth, let's say the bandwidth between the 5 and 95 percentile, and in the calibration period, and always in the validation one. And it increases also in this case, as expected, moving on with the time, increasing also the time lag. Just for completeness, I here presented the time series for the 24 hours of prediction, time lag prediction. For Punta della Salute in the bottom part and Lido di Pesud in the upper one, the observed data with respect to the expected value provided by the MCP and the forecasting given by the Scheiffen model. And now these are the main results, the focus of this presentation, because we applied also the MCP in the operational, we implemented it in our operational chain, even though it is still in a testing phase. And these are the main results. It is just an example of Lido di Pesud in the 3 of November 2021. And we decided to fix 3 thresholds, 110, 130, and 140 centimeters, moving from the left side to the right side of this slide. And in the first panel, you can see just the forecast given by the MCP with respect to observed data and the bandwidth between the 5 and the 95 percentile. But what it is really important is the bottom, the central and the bottom panels, because this is the additional information we are able to give to a decision maker that have to decide if to intervene, to act somehow, and he can do this in a more conscious way, because he can decide also what kind of risk to take, because we can give him also the probability of an event to exceed the fixed threshold, since the central panel represents exactly the cumulative distribution, probability distribution of the sea level, and the bottom panel represents the time of the excellencies in which we expect the excellencies to happen.
Thank you, sir. Can you come to the conclusion, Sarah?
Yes, I'm just moving on. This is in the case of, and this is in the case of Punta della Salute, and these are the analysis of the maxima we selected from November to 2020 to January 2022, and here are some main results. I just want to show this one because it probably is most important, and then I finished. These are the comparison of the cuckoo plot once more for the MCP with an advance of 24 hours and with respect to the Scheifen fed by with Bolam and ECMWF. And you can observe that the mean absolute error for all computed on all the maximum we selected, as I show you, it's always lower than the mean absolute error calculated by the numerical models. And so other diagnostic indexes. And now I'm proud about this work, and I'm happy that we just signed the new collaboration with Gabriele Coccia in order to implement these new steps about the increasing the calibration and validation period, the implementation of new data sets, also in collaboration with other institutions such as the municipality of Venice, and we are trying to feed the MCP with different components used separately in order to try to implement and to improve the performances of this model. Thank you very much.
Thank you, Sarah. There is no question, and we were a bit far in time. So we move to the next online poster presentation. So let's try to keep the 5 minutes talk. Iman, do you hear us?
Yes, I can hear you. I wish that you can hear me too.
Yes, very well. And now
Okay.
we check your poster. Can you introduce yourself in the meanwhile, where you come from?
Okay. First, I want to thank you for this opportunity. I'm Iman Jodar from Morocco, and I'm a PhD student working on the assessment of marine submersion hazard on the Atlantic coast of Morocco. So for my poster, it's about the impact of marine submersion on the Atlantic coast of Morocco. It's a case study of El Jadida Bay. The objective of our work is to study the risk of marine flooding and also assess the vulnerability of this city and by numerical models. And our study area is an area often flooded by high waves and storm surge. And the land use here show us clearly the residential area is very important near to the coast, which explain the vulnerability of the city. In order to study our set very well, so we adopted the IBER open source software. It's a software to solve problems involving different fields, such as flood risk assessment, and the quality of the results is quite depends on the input data set we introduce to this model. So as a result, IBER provide a map of water elevation and a map of hazard based on 3 classes of danger: high danger, moderate, and also low hazard. The simulation was forced by historical storm data for 2017 storm. That the water elevation map show us a significant variation of water elevation along the bay, and that help. You can show the results. So as I said, The simulation was forced by historical storm data for 2017, and that's the water elevation is have a significant variation of water elevation along the bay, and that's helped to understand the overflow water elevation and the vulnerability therein along the bay in order to protect the area potentially exposed to flood risk in the city from possible extreme events, and also involving the implementation of preventive action strategies in the city. And thank you for your attention.
Thank you very much.
Thank you.
Yeah, there is a question.
So thank you for this presentation. I don't know the software, but can you tell us the limitations that you feel what are the possible new developments?
So for the limitation, I think that's we have just an overflow with this software. We cannot have a wave propagation or also a very clear bathymetry with this software. So it's also depend on the, as I said, on the data set we have. So if we have a really good resolution, that's can give us also a very good results. And it's a shallow water model, so I think that's the limitation.
Thank you.
Thank you. We have another present. Thank you very much, Iman.
Thank you.
We have another presentation, another poster online, and then we will move to on-site presentation. Nualia, do you hear us?
Yes, I am. Can you hear me?
Yes, please. Yeah, try to talk and introduce yourself.
Okay, thank you. So, hi everyone. I'm Hela Rajahid. Currently, I prepare my PhD thesis in Said Karim University in Morocco, and I'm working in marine geoscience and marine modeling. So I had the honor to participate in this workshop, and I apologize for not being able to come on site. So today I will be talking briefly about hydrodynamic modeling of Moulay Boussaham Lagoon in Morocco, numerical investigation. So the Moulay Boussaham is located on the Moroccan North Atlantic coast. As you know, the lagoon ecosystems are among the most vulnerable ecosystems often subject to mixed situations, including a number of disturbances to the balance of the lagoon ecosystem in terms of hydrodynamics and sediment transport. So within the framework of this study, the analysis and evaluation of hydrodynamics and morphosedimentary process will make it possible to fill the gaps in the sedimentary dynamics in the Moulay Boussaham Lagoon, which was not yet completely understood. So we will present a numerical methodology to study the impact of natural process, sea level rise, well, etc. As shown in the diagram, the main research is based on the study of the function of the lagoon inlet, which directly influence the balance of the whole lagoon environment. So currently, this lagoon is experiencing a tilting up problem, which has led to the creation of a peak that has developed to the southern limits of the inlet. It has been shown that the migration of the peak towards the lagoon, accompanied by the development of a water delta, takes place during storm events, which are more than 90% responsible for its morphology, which tends to close. So this work follows the first application of the Mike 21 flow model, developed by the Danish Hydraulics Institute, to the lagoon in order to study the erosion deposition patterns of this lagoon through the application of numerical modeling and to stimulate the hydrodynamic circulation, but also evaluate the impact of extreme events on the sediment dynamics in the lagoon. So as shown in the description of the results, the change in the Munibushan lagoon, this lagoon are significant during the study period from 1949 to 2021. This period materialized by clear accumulation that affected the hydrodynamic exchange between the lagoon and the Atlantic Ocean, and what will lead to complex environmental problems thereafter in the lagoon, namely the loss of habitat and ecosystem health in general. And thank you for your attention.
Thank you, Nohalia. Thank you. Okay, I don't see questions, so we move to the next presentation. In my agenda is Stefano Querin from OGS. He will present a couple of hydrodynamic biogeochemical modeling for short-term forecast in the Northern Adriatic. Thank you, Stefano.
Good afternoon, everyone. Yes, I will talk about this work that we did at OGS, which is Italian National Institute of Oceanography and Applied Geophysics. We already talked about Copernicus, but maybe not all of us is aware of what Copernicus is. Does anyone know what is Copernicus, or doesn't know? All of us, more or less, I think so. By the way, it's the Earth Observation Program, European Earth Observation Program, so for the monitoring of the environment and to gather and provide information and data. It started with satellite observation, but then it integrated also models and in situ data. The paradigm is fair, so findable, accessible, interoperable, and reusable data, so open data to the scientific community and to the public. We have 6 services that you can see there, so climate change, marine atmosphere, land security, and emergency, and of course we will focus on the marine service, in which you can find on the website many products and also a very nice visualization tool, so to have a look at the products that are available on Copernicus. But there is a problem because I mean you can see the online catalog for the Mediterranean Sea, for example, for the physical and biogeochemical model and the wave model. So all the products are available and can be used and downloaded by the people. But if we want to go a bit more on detail, we see that the resolution is not enough because the model, the Mediterranean model, is a 1/24 of degrees, so more or less 4.5 kilometers. But if we want to go to coastal problems, this kind of resolution might not be enough. And so we try to do a downscaling, so zooming in Northern Adriatic. So we are again in well, a few hundred kilometers from here. So the modeling system in this case is online coupled. So we have the MIT. I don't know if you can see the pointer. Yes. Okay. So there is the hydrodynamic model. So the core of the hydrodynamical part is the MIT GCM. So the Massachusetts Institute of Technology General Circulation Model. And then the biogeochemical reactor is the BFM that we already have heard of. So the biogeochemical model for the lower trophic levels, so phytoplankton, zooplankton, nutrients, and so on and so forth. But all the other speakers before me already talked about this model. Then we have to couple these 2 models. So we developed this BFM coupler, so a system that make the MIT GCM and the BFM talk together. In between, there are other steps. So there is the transport model, which is this one, and then the integration in time. So the tendency from the transport comes from the transport model. The tendency from the biogeochemistry comes from the biogeochemical model. And so then you have the full integration in time. So all these models are open. So the MIT GCM, the BFM, the coupler, everything is open and is available for the users. And we also developed a nudging scheme for sea surface temperature and for coastal data of nutrients. So in a few words, the setup of the model. So we increased the resolution from 4.5 kilometers to 750 meters, more or less, with the 27 vertical layers on the Northern Adriatic Sea. And we, let's say, capitalized on our experience on modeling in the Northern Adriatic. So the atmospheric forcing now comes from two models. One is the Aladdin model from the Slovenian Environmental Agency, and the new one, the new one that we implemented. There is a long experience on the Cosmo model by the Environmental Agency of Region Emilia-Romagna, so an Italian environmental agency. Initial and boundary condition come from Copernicus because, of course, we are nested into the Mediterranean model of Copernicus. We consider the 19 major rivers flowing in the basin. For the Po River, which is the major contribution, we also have the real-time data. So we have a real-time flow discharge data from the Po River. And then all the other very important data. So the nutrient input from rivers, from the Venice Lagoon, from the atmosphere, from the bottom, and also from the sewage discharges. So the urban outfalls of sewage coming into the basin comes from literature, from climatology. So all the best data that we can find in the literature, in the several data sets. Here there should be a movie. Okay, it starts showing a website in OGS, this MEDEAF website, in which we publish these results. So OGS is in charge of the Mediterranean biogeochemical part of Copernicus. CMCC is working on the physical part, the HCMR on the wave model. So this is the biogeochemical part on the Mediterranean Sea, but then we want to switch to the Northern Adriatic, in which you can see, for example, the maps of, this is the forecast of today, so it was released today, the 11th of March. This is the 72-hour forecast, so we have 3 days forecast. You can choose variables, layers, and the time, and you can also have a look at the evolution of the system playing a movie. So it's quite simple representation, but it gives you an idea of how is the variability of the system, how the coastal current, there is a typical coastal current on the Northern Adriatic, how it behaves and how it evolves in time. Then we did some validation. Here you can see some plots divided into a coastal area. This is updated to the first day of May. So there is a coastal area, so shallower than 20 meters, the open sea deeper than 20 meters, and the whole basin. We have some time series for 1 year of chlorophyll from satellite measured in black, in green, and the output of the model in the black line. Then we have some bias and some root mean square difference, and the number of data coming from the satellite. And you can see that more or less we take the behavior of the general evolution of chlorophyll, for example. Then there are also the capability of showing some maps, so comparison between the model on the left-hand side and the satellite on the right. You can see some particular events. In this case, when there is a particular wind blowing on the basin, there are some interesting structures that you can see also even more in detail in the chlorophyll images. So you see some jets, some instabilities, some interesting shapes that are replicated quite well by the model. There is another event here at the end of, so this is a spring image, but there is also some winter event. So you can see there is this plume of chlorophyll-rich water, and also some other shapes that in some cases are also overestimated by the model. And one problem is sometimes we underestimate the coastal values of chlorophyll, and this is a problem that maybe we can discuss also later. This is the second version of the model, forced with the Cosmo atmospheric model. So there are 2 versions. Let's say our goal in the near future will be to have some kind of ensemble, so coupling the model with, yes, an ensemble modeling, so coupling the physical model with several meteorological models in order to have 2, 3, 4, well, it's a reduced ensemble, but you can have an estimation of the variability and how the model behaves with different forcings. One last recent experience that we had, Aldo Drago is also here, was part of the game in the ShareMed project. We developed also this system in a relocatable way, in the sense that we tested in the Northern Adriatic, but then we exported the model in the Sicily Channel and other 3 transnational subbasins in the North and West Mediterranean Sea with different resolutions. And so this system in some cases are survived also after the end of the project. So for example, for the Catalan Sea, the ICATMAR, the regional Catalan agency for environmental protection, has adopted this model as its own official model for the forecast. So to conclude, this Northern Adriatic forecasting system, we called it NARF, gives daily updated forecast with 72 or 48 hours, depend on the Aladdin has 72 hours, Cosmo has 48-hour forecast. So we can see some fine scale structure that of course cannot be seen because of the resolution on the Bayesian scale model. And then in the framework of this MED program, ShareMed, we developed also the repeatable modeling system. So all this software is available, it's on a GitHub repository and can be used and downloaded. We are refactoring it in order to make it a bit more user-friendly and more usable, but it's there. Last slide on the further improvement. We wanted to go in the framework of another national recovery plan, INEST. It's an ecosystem project, is in the category of the ecosystem project in the national recovery plan. We are going towards the digital twin of the Northern Adriatic Sea. So merging together experimental data, numerical models, artificial intelligence, which is let's say a new entry, quite recent tools in oceanography, let's say. A big data repository for all this data. We call it data lake in a fancy way, but it's a data repository with some peculiar features, and then visualization, of course, and interactivity for the users. And yes, last, many people to thank because we interacted in many projects and we had a lot of collaborations, and so there is my name in the presentation, but a lot of work has been done by many colleagues and with nice interactions. And I thank you for your attention. Yes, thanks.
Thank you, Stefan. I have one question, and then while I walk to Aldo, what is the difference using a high resolution atmospheric modeling and the lower resolution one? How the ecosystem modeling behave differently?
We have to check because let's say the 2.2 kilometers of the Cosmo compared to the Aladdin, which is let's say twice, Cosmo is twice the resolution respect to Aladdin. It's running since 10 days more or less, so we have to check the results and see how it behaves. We have still to tune the system, but now we set up all, you know, the download system, all the automatization and stuff, and then afterwards we are. But we expect some good news from that implementation. Yeah.
No, just wanted to thank for this nice presentation, even because as it was mentioned, we have experienced the professionality of this work. This is a big capital, and my question to you is whether the future plans could embark into exploit this big capital, in the sense of, he was mentioning the relocatable geochemical model, which is an existing experience, not experimental. It's existing. It can be done with little effort, of course, but having the resources to export it to other places. And to export it not just to do the job for other countries, but to join the countries in a transnational manner to do these implementations in a long-term perspective. And I wanted to have an idea about any plans that there is in this sense.
From me. So in our idea, we are working to go on, and this code refactoring is going on in order to have it even easier to implement and to install in the system. So our idea is gone with this. Another tool was the auto nesting. So we have a regular grid model. So if we want to go further in detail, we have to do further nestings. And so since the model it's automatic once in a sense, it can be quite easily go and nest onto itself. For example, we were talking about the Sicily Channel and the Malta Island. So that's the next goals of these activities. I mean, we are linked to the regular grid. So then is the big question whether it's better regular or unstructured, and we can discuss it at the break.
No, I mean, this is clearly a very important work, because for the first time you can show that a complex ecosystem model can be relocated in a rather simple way.
Then
Yeah,
some
you know,
tuning are still needed.
And what we need in Cost Predict is to finally write down what you need really to relocate. So it's okay. Now we do it in 1 month to relocate because we need to do all this tweaking. We have to write it and make it available as the nowadays knowledge, and maybe with Cost Predict to advance. So one question is, I find that when you go to this scale, it is very important to understand what is the dimension of the domain that you use, right? So especially in the structured grid world.
Yeah, I mean, you are limited to, I mean, the resolution that you wanted, the width of the domain that you can have, I mean, compared to your HPC resources as well. So there is a trade-off somehow between these two limitations.
So mainly we are limited not by science, but by computational resources when you do this.
In some cases, there is also new models, Oceananigans is coming out, written in Julia for GPUs. So other new possible, and it's the same community of the MIT GCM. So maybe in the far future, let's say medium term, it could be an option. So switching to GPUs, so much more performing. This is still Fortran 77.
Yeah. And the last comment I wanted to say is when we will present the global cost experiment, the answer to Aldo is that we want to really have not only data stored in a data lake, but also the tools and have adequate interfaces for users to use. So this experience is one, and there are others for unstructured grid and so on. So I think that the direction is that we make available also the tools, not only the data in the global cost experiment in the different areas, and that will allow for this experience to amplify and become more visible.
Something like MyOcean Pro and tools like that. I mean, very, very easy to use and powerful and fast.
No, just a quick question. You went very fast over the performance of the model. That seems to me not fantastic. So any plans, you know,
yes.
Why
one
is that?
big,
because
one
before
big
going to the GPUs, you know.
Yes, one big issue is the initial condition, because we every time we reinitialize the model from Copernicus, we have a 1 week of spin up, and then we let the forecast go. And now we are working with the artificial intelligence department of the University of Trieste. We have 12 years of reanalysis of this model, and we have the same 12 years of Copernicus. So we make the artificial intelligence model, we train it to replicate the reality, which is our reanalysis. We consider it the reality. And so we could start from initial condition closer to reality with a correct concentration of chlorophyll or nutrients that cannot be absorbed in 1 week. I mean, physical dynamics are much faster, biochemical are. So for sure, one problem is the initial conditions. We will try this approach, and also the parameter and the bottom fluxes of many other actions to improve.
Okay, thank you. Now, before closing the session, we have a poster and the presentation. Right? So Italo Lopez, yeah. Anybody else? Yes, Simone, please.
Well, good afternoon. My name is Vitor Lopes. I'm a PhD student from the University of Bologna, and this is part of my PhD thesis. That is the development of a coastal modeling system for flood prediction. Sorry. So we aim to develop a relocatable system and also standard calibration protocols to accurately. Okay. Okay. Thank you. And also to create standard calibration protocols for flood modeling. We are using the least flood FP model with the acceleration solver and 50 meters of resolution. In this case study that I'm showing is the flood event of February 2015 in the Emilia-Romagna region, which at the time was one of the highest records in the region. Okay. So as input data for the model, we are using the digital elevation model provided by the region, the many coefficients fields, and the water level data from the Porto Corsini station from ISPRA. And as output of the model, we have hourly and maximum water depths and the flooded areas that we can compare with the observational data from the inundation maps of the region. So showing a little bit the results. This is the maximum water depth from the model, and the red line is the inundation map of the event. So we can show that most of the coast we can represent well the event. But there are some areas like here in Lido di Dante and Lido Adriano that we have an overflood of the model. We studied different ways of running the model using also different digital elevation models. And also this area is the area that the elevation models has the most discrepancies. So we believe there is some there are some local characteristics that is related to the overflood. So as future steps, we are simulating more events in the region. We are also using another forcings. Now we are using only water depths, but we are also implementing the river and precipitation data in the model. And we are trying to create the protocols to calibrate locally the mean elevation of the digital elevation model. Also try different elevation models, and also to best fit the many coefficients using the land data, the land use data, and the digital elevation model information. That's it.
Very much. Congratulations. So I have a question. When you present the left panel of the results, you call it inundation map. These are observation.
The red line is the inundation map.
Okay. So these are observed in situ inundation area, inundated area. Okay, no, it's good. And okay, yes. And as boundary condition, what are you using? I mean, what is the input for the least flood as boundary condition? Maybe you said that.
Yeah.
Is the Porto Corsini tide gauge or?
Yes, we use the data in Porto Corsini tide gauge, and we put as input in the coastline, in the whole coastline.
Okay, yes. Thank you. Any other question? No, then thank you again. Then we move to the last presentation of the session, which is Mahmoud Hassan from University of Bologna. Please, Mahmoud.
Hi, everyone. Good day and buongiorno. I'm going to present my part of my PhD thesis, which I have produced with the continuous guidance and consultation with Professor Nadia Pinardi in collaboration with CMCC. In my presentation, I have two parts. In first part, I will present the reassessment of the heat budget in the Mediterranean Sea. And in the second part, I will present the investigation results that we retrieved some extreme values from the heat flux that I have computed in my first part. So for just a little bit of the ERC fluxes, to compute a net heat budget, we need four components: the short abbreviation, long abbreviation, and the latent and sensible heat fluxes. The ocean interacts with the atmosphere at the ERC interface continuously by exchanging heat moments, water, and heat fluxes. So to compute the heat budget, we need four components. These, for example, the short abbreviation. So for the Mediterranean, we have this formula has been adapted by the previous researcher. So we are applying this formula to compute our heat budget. So for example, short abbreviation, we have two conditions. If the cloud fraction is more than 30%, then we have one condition. If the cloud fraction less than, then it is another condition. And for the long abbreviation is the difference between the infrared emitted from the ocean surface and the atmospheric downwelling infrared radiance. For the latent and sensible heat flux, we need mainly three variables: atmospheric, wind modulus, and the sea surface temperature and the air temperature. And other coefficients we use as a constant values for this that has been referred into the literature by the other researchers. So in the Mediterranean, why Mediterranean? Mediterranean is one of the largest complex sea basin, and it has numerous islands. So due to its orographic features and the existence of narrow Gibraltar Straits, it always impacts the distribution of the heat fluxes. So there are a great number of studies have been published in the last few decades, and the result, it has always been a difficult one to decide on a very reliable or predictable net heat budget. So anyhow, for this study, I have used two data sets. First of all, the atmospheric analysis data set retrieved from the ECMWF, which has a 4 daily time steps and the spatial resolution of 0, 1 to 5 degree. And another one is the ERFF reanalysis data set. Both data sets have the same variables: mean sea level pressure, air temperature, dew point temperature, and the zonal and meridional wind components. But to compute the heat fluxes, we need the SST. The SST has we have selected the level 4 SST products, which has a higher resolution, but it has been transferred into the similar grid to the atmospheric data set. And in the map, we show that there are 8 sampling locations that I have selected to initially to check the time series of this of my fluxes, that how we can see initially how our statistical PGF can be fitted well or bad on these points. So then we have computed in the left panel, we have the climatology of the heat fluxes from the February and August. As we see, there are the significant differences, spatial variations, especially in the latent heat. And for the sensible heat, we can see that some variations especially in the Aegean Sea. Otherwise, it is very clear that seasonal variation is very distinct in favor for the long wave and the shorter variation. And then we have computed the net heat budget beside the ERF5 dataset. So in the ECMW dataset, that's the higher resolution dataset, and so we can see most of the sensible heat flux, latent heat flux, and even the shorter variation. They are very good agreement in the distribution, except the long wave variation. We see a very separable difference between these two data sets. And for the ECM data set, the mean latent heat very value is almost 100. In the for the case of ERA5, it is around 81 or 82. So now then there is a net heat budget, and in the first left panel for the February, and we can see the net heat budget in the February. We consider as a winter period, and the summer for the August. But for the annual heat budget, we see clearly that the Western Mediterranean is losing more heat, as because this part is influenced by the Atlantic salt and saline water, and that actually that means that in Mediterranean is losing. In general, hypothesis is that Mediterranean should there should be a negative heat budget. Yes. So in other sense, we can see two other features in the Alboran Sea part, that blue area, and also in the Aegean Sea. We believe that there could be a possible relationship from the local winds, like the Mistral winds that blows from southern France to the Alboran part, and the dry and cold wind, and in the Aegean Sea, the summer winds, it blows in the Aegean Sea around the Greek islands. We see the influence of these two local winds very clearly. So now the questions that I said, we have a issue that why we have different values in the literature. For example, over the last few decades, there are many studies, and they have produced different results. We can see the variation in the net heat flux, either -6, 20, -7 to 29. So there is no very constant values in close range. In our case, for the high resolution data set I have produced, that net heat budget shows the -3. But interestingly, the ERF data 5 data set, which have a lower resolution, which shows a very positive net heat flux and very large difference. You can see that. And the difference, of course, I mentioned my previous slide, that is in the long wave radiation. So then the statistical analysis, it has been a kind of new approach for the Mediterranean Sea. Several researchers have already mentioned the importance of a statistical analysis on the heat fluxes, but there is no dedicated study. So anyhow, so in this plots, I can show that 8 points that we have fitted with the asymmetric Laplace PDF, because we have observed 2 double peaks. We cannot fit in the Gaussian one, because we in our transformation data set we can see that there is 2 peaks that are fitted with the atmospheric data set. And the data set before processed with the by subtracting the seasonal climatology that is produced by this equation, then the long-term anomaly is computed following this subtracting the anomaly addition. Then based on that single grid point, we have computed we have produced a spatial map for the parameter distribution for the shape, location, scale, and then we have compared with the reconstructed moments from the theoretical moments. So we can see that mean and variances are very in good agreement, but skewness and kurtosis have very significant differences. And then the latent heat flux we have fitted with similar way, like sensible heat fluxes. We have fitted with 3 parameters, but in that case we can see the distribution is it's almost Gaussian. So, but there are some tails existed. So in that case, we have applied this normal distribution. And the similar way, we have fitted, we have produced the parameter maps of the parameter, and that we compared with the theoretical moments. And we can see there is still this skewness and kurtosis are in very big difference. So then we have applied a chi-square test. We see that some parts are not a good agreement in between some of the regions, latent and susceptible heat. And yes, and the yellow That means we have set values for the 95% significant level as 34. If the values, if chi-square values are below this, so we can consider this point the fitted fit is well. And then the second part, I will present the extreme value theory. As we have seen that we have some tails, long tails that so we believe that there could be a possible extreme values in our time series. So, and this tool is one of the very useful tools to model the extreme values. So we parameterize using the extreme value theory. And in there, most common approaches are block maxima or minima or the peaks over threshold. But when you consider generalized extreme value cases, so we consider the block maxima in our study. So for the block maxima, we divided our time series in a very equal range. For example, in my case, I divided into monthly for my all 20 years time series. Then I retrieved all the extreme values. So here I can see that all the red points are the extreme values from my sensitive heat fluxes, and this is the time series of the that extreme value time series, and this is the previous fitted with the asymmetric Laplace that I showed previous. Now this is the extreme values fitted with the general GEV PDF. That's a generalized extreme value PDF. And in the same way, the GEV has the 3 parameters: shape, location, and scale parameters. And in the lower peak, it is a similar way. I have retrieved the extreme values over for the latent heat fluxes, and we can see that time there is a very fluctuation, linear fluctuation in the latent heat fluxes. And so in this for the 8 points that we have selected, a similar way I have retrieved, and we can see that our GEV model can fit well for the sensitive fluxes most of the cases, even though some few points maybe we have still some very extreme high values. It could be obviously we need to investigate why there is some very extreme value. And then the same way we same 8 points. In this case, we see that the fit of the GEV on the latent flux is not very well, because we can see there are very many fluctuations in our almost of the points. So I think we will see
conclusion.
Okay. So in addition to that GEV fit, and we have done a clustering analysis with a hypothesis that if there is any relation between maximum minima distribution, or if we exclude all these extreme values, is there any impact on the net heat fluxes? So the cluster 1 and cluster 2 here. So we can see the cluster 1 and cluster 2 results. We can exclude this cluster 1, cluster 2 from our net heat budget that we plan for the next stage. And similar way for the latent heat fluxes, cluster 1, cluster 2. So okay, in conclusion, so I will follow on the next steps. So next step we'll try to explore these extreme values from our regular time series to see if there is any considerable variation in our net heat fluxes. At the same way, if there is any possible relationship with the minimum and maximum values. Why I'm interested? Because we can in this way, this knowledge can help us to compare our and to compare with our prediction that is the developed in the being in the uniform CMCC. We can check if our because this prediction motion forecasting system also produces heat fluxes, so we can see our results really merge with this our PDF and other distributions. I think that's all. Thanks for your attention.
Do we have any question? I have one. I mean, does it make sense to do this analysis? You selected some points at the end, and you focus on those points, but to do it, to distinguish the coastal strip, maybe with bathymetry, and the offshore, so to understand if there is Because you mentioned at one point, for instance, the wind effect that was coming from land to
Yeah.
the ocean, the signal. So maybe is there some features that distinguish the coastal atmospheric fluxes with the offshore one?
You mean the particular points? But
Coastal strip and
Oh,
analyze the same.
no, because we have seen that this distribution, this feature is very significant in this area. And because I've not presented the wind vectors, that is my first part of my PhD. So there we can see that this wind is influencing this part. And these winds are very well known in the Mediterranean region. So if we overlay this wind components over this region, so we can make a connection over these two areas. So, but as I did not present the first part, so sorry. So maybe.
It was clear, but for instance, there was I was checking with Nadia. There was in the south of Sicily, a clear signal of probably upwelling process. So this would be an ocean coastal process that affect the atmospheric fluxes. So maybe in some other areas you have a coast, like you have the interaction with the rivers that might influence it. So the question.
Yeah, thanks for suggestion. Maybe I will investigate more in the next step. For the offshore area and for the coastal area. Oh, of course. I can do it any part where there is water or sea. Yeah,
exactly.
Yeah, and therefore the coastal area. Yeah, of course. Okay.
Well, then we gave you ideas for future work.
No, of course I can do, but that point I have selected is just randomly. But if I have in particular interested area, I can do that. Of course.
Okay. Now, yes, please, Slim.
It's so about the extreme value analysis. So normally you can so identify the so return period depending on the so amplitude of the event. So can you classify now? So according the area that you have chosen, what are the areas that are more exposed to this extreme events?
Yes, actually, yes. Due to shortage of time, I did not produce that return period. So I've already doing this. Hopefully, I will do the next step. So then I can see the comparison, which part of which area, which more values are extreme values are coming there. Yes, I can do.
Thank you. So now, just to get organized, we stop, we go to the coffee break.